This conference will now be recorded.
Okay, here we go. We are online now. Hi, everyone. Today we have Ben from Google is going to talk to us about the open chiplet specification.
Mm-hmm.
That's
yeah.
pretty much on topic for today. If at the end of the meeting we have a couple of minutes, we may talk a little bit about white paper. If not, we'll talk about it next week. The agenda for next week is basically to work on the white paper. And in 2 weeks from now, tentatively, I have James to present to us on the ZEF format, the XML version of it, and see how that work is going. So that's about it for me. Would anyone like to bring up a topic, a different topic, something else would like to discuss today? Nope. Okay. All right, Ben, it's all yours. Wait, I think I need to click to a button to make you presenter, right?
That's right. Yeah, I was just going to ask for that. Thank you.
Okay.
Okay. How does this work? I see. Okay.
Yeah.
Okay. So the what I was going to share. How's that working? Did that share? Okay. We don't use this internally. Can you see the slides? Is that working?
Yep.
Yeah, we see your slides.
Oh, cool. Okay. All right. So let me introduce myself. I'm Ben. I'm an ASIC engineer at Google. I've been with Google for about 3 years. I work in an ASIC team that is focused more on internal sort of silicon projects, mainly for use, within Google's organization. Because as you know, Google's not well known for selling silicon. So yeah, we obviously develop silicon for our own internal use. So this is a slide deck that Rohit has already presented to the OCP community. I think he did it a week ago or so. Okay, and let me just maybe. Okay, all right. Yeah, so he presented this slide deck a week ago. I'll go through the slides again, maybe in not quite so much detail in case people have already seen these slides. And if feel free to stop me on anything interesting. And then if we have a bit of time, I can maybe also show you the actual spec and how to access it on GitHub. So I think we all know why we're here. Probably, we're obviously developing chiplets as a way to extend sort of the extenders past Moore's law, I guess, to some degree. Obviously, trying to limit the size of monolithic die, fragmenting silicon into smaller chiplets obviously gives us better yield, reduces the cost of the individual die. Comes with complexity from having to implement more advanced packaging solutions, but the industry is quite well ahead in terms of dealing with multi-die packages. I guess industry's been making those for quite a long time in terms of sort of SIPs, the traditional sort of multi-die on an organic substrate. I guess recent advances have pushed us into 2.5D sort of silicon interposer technology, particularly driven by HBM memory and Xilinx as well. And so again, chiplets has a very nice application with silicon interposers, and and then it forwards into sort of true 3D stacked die as well. So I think that's an AMD CPU there. Yeah, AMD have definitely opened up the whole chiplet area. But yeah, I think it's been around for quite a few years, really, since Xilinx sort of really pushed it forwards. Okay, I guess Google has been a member of OCP for a while. Sorry, this is Rohit's slide. I maybe should have read it before I started. I guess it's kind of saying the same thing. Silicon technology is obviously improving. We're getting smaller transistors. Those smaller transistors are coming at quite a cost. We would obviously like to take advantage of those technologies as best we can. And I guess if you look at process development, it focuses a lot on SRAM and sort of digital logic as the real driver for qualifying those process nodes. But typically coming along with it, you want sort of complex analog IPs, SerDes, PLLs, those kind of things. And those IPs are pretty tricky to develop. I used to work in a SerDes development team for Texas Instruments once upon a time, and it takes quite a few iterations to get SerDes right on a new technology node. And so I guess chiplets is also a way of kind of de-risking some of that newer technology processes. You can certainly see a lot of commonality in various commodity functions. If you take something like PCI Express, it's a very well-known PHY. It's extremely common across a lot of products. It's almost a ubiquitous kind of interface in the same way maybe USB has become as well. So certainly opportunities for chiplets to kind of commoditize those sort of very off-the-shelf standards type interfaces. Ethernet maybe as another example as well. It's sort of another area where I guess chiplets could potentially help out there as well. And of course, as we do start to disaggregate the die, we have a need for a die-to-die interface to kind of move high bandwidth data on and off, obviously, between dies. I guess the industry knows how to do sort of low speed, and then OCP and the ODSA are certainly developing a couple of sort of high bandwidth PHY options. Sorry, was there a question? I guess not. Yes, and I guess chiplets in particular is definitely gaining momentum. I was actually a speaker at the business workshop in April, and sort of grabbed some statistics from that particular event. And yeah, I think it was one of the largest attended workshops in OCP history. So there was certainly a lot of interest behind chiplets. And I think one of the messages from that sort of workshop was really that to enable a chiplet ecosystem and a chiplet marketplace, you really kind of have to break the circular chicken and egg problem. Companies like Google would like to buy chiplets, particularly in those sort of commodity areas to allow us to focus on sort of our special sauce, and I guess not have to redesign and requalify sort of standards type interfaces over and over again. But of course, we can't buy those chiplets until chiplet suppliers see a demand to actually go out and create those chiplets. And again, chiplet suppliers, want to see volume from this space as well. So just Google going out and trying to buy these chiplets probably doesn't really add a substantial amount of volume. But I think if you take, again, using PCI Express as an example, if you take that interface and sort of amortize it across the sort of however many hyperscalers and other customers that could potentially use that chiplet, then you could see the volumes getting pretty substantial. Obviously, higher volume means lower cost for everybody. So, enabling an ecosystem, I think, has general benefit across the industry. But of course, the chiplet suppliers don't really know what to make. So in order to break that loop, I guess we realized that trying to put everything down into a sort of chiplet specification would really kickstart the industry. even I guess I was looking at it almost like TTL logic back in the days of 7.4 TTL logic. Obviously multiple suppliers made TTL 7.4 series chips, and they were kind of built to a common JEDEC specification. This probably doesn't necessarily get up to JEDEC, but I think at least a sort of a means to kind of at least capture a common set of requirements into a specification would start to at least get the ball rolling. And so the solution that I guess we came up with internally was to really create this open chiplet specification. We worked on it internally for a while, and then essentially got the go ahead to open source it and release it on GitHub. So the spec is out there. It's at a 0.1 release, so by all means nowhere near complete. But really, the motivation to open source it was to gain collaboration from the general community, particularly OCP and ODSA members, and having sort of recently attended seen your white paper as well. I think the CDX team could really help in this area as well. The chiplet spec that we've written is Rohit calls it kind of full stack. So we really take into consideration from a sort of software API through to some of the hardware on the chiplet, and then through to sort of trying to set some physical constraints on what the chiplet should look like. Of course, we're not building TTL chips, so we can't sort of we can't rely on 0.1 pitch pins and that kind of thing. But at least trying to get to some commonality across the footprints, but also accepting that variability. Nobody wants to be giving away silicon with nothing on it. So we'll see later that the footprint kind of does have scope to at least adjust the sort of square millimeters. And particularly the sort of manufacturing testability, I think, is an area where CDX could really help out. So kind of okay, yeah, just kind of stating what I said there, that we feel that this specification could at least start to get things rolling, and I think also looking across what ODSA is doing, there are lots of pieces all in flight. We have the Bow PHY in flight. We have the Open HBI PHY, obviously the work from CDX, and a link layer kind of development as well. But I guess nothing really to tie all of that together into a final sort of almost product spec or something that kind of glues all of those work groups together into a single sort of overall specification. So I think that's kind of the vision we had for this open chiplet spec, and of course developed in the open so that it's open for contribution. Certainly try leveraging as many existing standards as we can. Something like PCI Express again is we're definitely not looking out to redefine PCI Express. I think we would just reference it for the sort of PCI Express type operation. The URL for the project is hosted under Google's GitHub sort of repository, and there's the URL there. So if we have a bit of time, I can quickly browse up to that site and just show you what you get if you clone that repository. Again, we're trying to make it as broad as we can, so we're trying to address as many sort of chiplet use cases as we can envisage. We probably didn't cover them all. On the left there is sort of an IO style chiplet die with a high-speed interface layer. We deliberately don't go and say what chiplet that could be. I guess we looked at it as a layered sort of specification, much like IEEE sort of 802.3, those kind of specifications. Try to try to break up the components into layers and have those layers talk to each other, or at least present common APIs. And the main layers that we created really were the OCML, the open chiplet, management layer. Within that, a security agent. We'll talk about security in a bit. The build layer, which we really use to encompass everything to do with creating the physical chiplet, and again, the sort of CDX white paper really fits well into that layer there. And then also a sort of power and electrical layer, just to try to lock down some of the sort of electrical aspects of the chiplet. And then, yeah, like I said, 3 different applications: an I/O type chiplet. So really, data comes onto the chiplet and then exits the chiplet via another means, and more of an accelerator kind of, or sort of co-processor, or almost kind of chiplet, where obviously we push data onto the chiplet, something happens to it, it gets crunched, sort of modified, and then pulled back off the chiplet again. And then, yeah, I guess these are some even more exotic cases, maybe sort of wireless or even analog type interface chiplets as well. So really, I guess trying to cover a pretty broad range of concepts. Sorry, the transport layer. Oh yes, sure. Hi.
A quick question. So in this diagram, some of these components are going to be actual on-chip components, and as far as the way I'm getting it, some of these are kind of like a logical components where you mostly would deal with models rather than actual chiplet specification implementation.
Mm-hmm.
Right? Do I get these diagrams correct? I'm not sure if my question makes sense.
Yeah, that's right. I mean, I think as part of this specification, we would, I guess, reference everything to do with a customer like Google, taking the chiplet. Obviously, the silicon die is the end product, but we can't do much with that silicon die without a whole lot of models behind the scenes to enable simulation, enable thermal analysis, enable all of the steps involved in integrating a chiplet into a custom sort of system product. So yeah, there's definitely scope for a whole raft of different models, I think, to really enable the ecosystem. And
all right, thank you.
Yeah, I think that would be, again, part of the expectation of engaging with a chiplet supplier, is that they would obviously be supplying known good die in a sort of model that the industry already knows, but of course, yeah, enabling design in using all of the usual collateral that you would expect to get with a sort of pretty complex silicon product like this.
Yeah.
Okay, a quick dive into the layers. So I guess the main one that I think Google really wanted to focus on was the sort of management and software API layer. We really see this as a sort of plug and play type system. We wanted the ability for a chiplet based system to really almost operate a bit like PCI Express or USB, in that we have a sort of a management agent residing on the PCB, which wants to go out and discover what components are actually installed on that PCB, and so we open up this kind of management layer, very much like perhaps the PCI Express bar system. If any, I'm sure many of you are familiar with that, or the magic involved in Windows when you plug and play a new PCI Express card into a PC system. So yeah, this is this was sort of the vision here. that of course it's got to be extendable. We can't predict every single one of the type of chiplets that could be made in the future. And so, yeah, really putting together a sort of software type API which allows for discovery, and then also the basic sort of telemetry and monitoring type data that we would want to extract from the chiplet as well. In Google's case, these chips could be going into a data center somewhere, and for us in particular, monitoring and sort of health of the system is particularly important to us. So we definitely focused on being able to obtain telemetry type data from a chiplet. And so highlighted on every slide, areas where we certainly would like additional contribution from whoever is interested in taking the spec, and certainly working with us to kind of to build out the spec. The next really important aspect that again we focused on is certainly the sort of security side of it. I don't think we see that ODSA is really addressing security. Formally, I think it's been talked about in a few sessions. Certainly at that April session that I attended, security was touched on. But again, from Google's point of view, knowing that we trust and believe the chiplets that we are installing onto these products is certainly very important to us. Obviously, the whole assembly of chiplets goes to ODMs. Is that the correct word? I think so. No, OSATs. That's right. Yeah. The packaging houses. They're kind of the crux of assembly in a chiplet ecosystem, and of course, that they could be procuring chiplets from a sort of approved vendor list or something like that. And I guess we're certainly concerned about counterfeit or unexpected chiplets getting into that supply chain. And as I say here in a couple of bullets, it's a pretty high value attack surface if depending on the chiplet type. And a chiplet like Ethernet, maybe sees all of the data center network traffic going through it, or sort of a die that processes data could be processing user data in that situation. And so we care a lot about that, and we certainly want to be able to trust that the chiplets that got assembled by the OSAT are the chiplets that we were expecting to be installed, and they came from the suppliers that we were expecting to procure them from. We will implement a sort of airport style model where you've got to pass through security, i.e. you've got to authenticate the chiplet against some cryptographic type handshake functions to certainly believe that is the chiplet die came from where we expected it to come from. And of course, any security model really needs a lot of scrutinization, to look for holes and everything else. So definitely some scope to collaborate there as well.
So Ben, this security, checking the security, is that done by the system inside the chip, or is that done externally by polling each of the chiplets?
I guess I think it really depends on the application. In Google's case, we kind of push our root of trust, to a certain point in the system, and so we have a sort of TPM style chip, which we obviously trust inherently, and I guess that would be the entity that's responsible for ultimately authenticating the chiplets as well. And I guess in our case, that function kind of resides somewhere in the system. It could reside within the packaged part, assuming you've got CPU type resources on there and everything else, and maybe you trust the supplier of a sort of bigger chip compared to the sort of chiplets, like I said, in a commodity type market, you're maybe buying chiplets from multiple suppliers, and maybe they are the lower cost kind of commodity products, whereas perhaps you're assembling those on a ASIC die that you made, and sort of you maybe have better control over that particular part of the flow.
So is there standard IP out there that chiplet manufacturers could easily integrate into their chiplets, or how does that work?
Sure. So I guess various other standards have tried to solve this in the past. Is it PUF? I think is an example of a sort of authentication type mechanism, which I think went into Zigbee, or one of the sort of home automation type protocols. I think is an example of a way to do cryptographic handshake, in a relatively simple but scalable way, I suppose. I don't think we certainly haven't got to the point of locking down a particular handshake mechanism or anything else, but it would be along the lines of a traditional public key encryption kind of mechanism, I suppose. Exchanging exchanging keys, checking those keys for validity, checking them for checking them against a company like VeriSign or something like that, who kind of authenticates keys, that kind of process, I suppose. I guess it obviously implies an internet connection in that case, but yeah.
I think this is an important concept, and this is something we really haven't looked at in CDX. So it's something that if nobody else is looking at it, we probably need to consider this.
Yeah, it could be interesting. Yeah, I mean, I think it gets pretty deep into the sort of cryptographic kind of functions. Certainly a true random number generator type IP is the kind of things that I think you would need to be able to support this. But yeah, this really looks at a higher level, I think, in terms of what is the exchange mechanism, and how do we do that? Also in a silicon kind of workflow, where potentially chips get reworked, and maybe die swapped at certain points in the life cycle of a product, that kind of thing. So it isn't necessarily set in stone from the time of manufacture. It almost maybe has to deal with a little bit of change through the sort of product life cycle.
Yep, that's an important topic.
That's right. Yeah. Very quite application specific, I suppose, but again, an important thing that we really wanted to touch on. So the build layer, like I said, I definitely gets closer to the hardware and starts to really define a lot of the common sort of silicon ASIC style functionality that you would expect to see on a silicon product, sort of JTAG boundary scan, sort of testability. I guess we were thinking of some kind of functional BIST self-test mode, essentially to be able to go out and check that the chiplets are operational kind of in system. Not obviously the chiplets are being tested at wafer and everything else, but we were also thinking that being able to check the health of the chiplets at in system would be useful as well. Sorry.
This is Joe. This is my area of expertise.
Oh,
so there are a couple kinds of BIST. The first is logic BIST, which uses pseudo-random patterns.
Mm-hmm.
And by the way, you could check it. You could do a checksum of those patterns and get your encryption key, or be able to tell if the netlist has been messed with in any way.
Yeah.
But that's one method, and the other method is with memory BIST, where we can actually run and test all the memories in the system. We can do incremental repair in the system if a bit fails while in 2 years down the road. You can map in spare bits and self-healing kinds of structures.
Yeah, and I think we would also look at the the die-to-die interface as well, and try to recover those particularly silicon interposers are kind of prone to manufacturing defects that you maybe don't want to lose too much yield because of those kind of assembly issues.
Right.
And
for
then,
parallel interfaces, you can do scan between devices. You can do FTP captures.
indeed. Yeah, exactly. IEEE
Those kinds of things.
That's indeed.
Yeah.
All of those.
Or 1838. Yeah.
Yeah, that's right. Yeah, I mean, I guess the automotive industry solves this, probably, in a much more robust way than I'm familiar with. To be honest, I've never worked in that industry, but yeah, definitely, these I guess these kind of techniques exist, and a sort, so as you said, a logic-based kind of test, or some functional vectors or data between the two. Like loopback type patterns or something like that. I guess just some way to periodically make sure that the chiplet is still doing what we thought it should do when it was brand new.
Are you also covering 3D here, or are you kind of?
Yeah, I guess that's interesting. I think we were thinking more traditional planar. I think that as the first pass, I don't think there's anything to stop it expanding to 3D. The if you think of something in the 3D space, so if you thought of sort of SRAM or something, I'm thinking what kind of things might you procure. But yeah, SRAM stack or something like that on top of a main die could be quite a useful commodity thing. You're just literally buying SRAM type chips or even DRAM that you can solder on top of your sort of main logic die. That might be another nice thing that you could go out and essentially commoditize. And I think we see a potential for competitiveness as well, in that you could define power envelopes, but that still gives scope for I guess chiplet vendors to have value add. Vendor A and vendor B could do different power, the same function in less power or something like that. So I guess we wouldn't be dictating certain process nodes or anything else. It would be a spec with a power envelope, and room for innovation, I guess, is what I was trying to say. There's if you can find ways to, in the case of an SRAM die, maybe double the SRAM for the same space, then that might be interesting, something like that.
So Ben, is there an expectation in the specification where the chiplet vendors would provide the full production defect type test, the DFT test for each chiplet?
Yeah, I see what you mean. Obviously the chiplet are being supplied in a known good die type model, so obviously the bare die that the OSAT is receiving have obviously been through a KGD style test, but actually that brought me to an interesting discussion in one of the OCP meetings. You start to think about yield and almost liability, or if you're procuring these commodity type chiplets, perhaps if you have an agreement, and the supplier is giving you known good die, and then you receive those die, you assemble it, and then during test you discover that die was faulty, then potentially that die could be taking out a pretty expensive sort of finished packaged solution.
Yeah, we've had this discussion before.
Oh, right, nice. Yeah, I see. And I guess to me, it comes down to sort of risk and liability, I suppose. Or if you might even have the same chiplet product and you're supplying it to a few different people, but that chiplet could go into, say, a $10 part, and in which case your liability, is just $10 if you happen to take out that part. But if it goes into, say, a $1,000 solution, then you might not be so inclined to charge $3 for that chiplet. You might, because obviously your risk level is much higher, and so
I suspect it's going to work the way the IC/IP model works, where IP vendors they're not going to provide a liability for the cost of the system. They'll just fix the bug if there's a bug, and they'll limit it to that.
Indeed,
so
that's right.
If you put a $5 part and you have a $2,000 SIP, they'll fix your $10 part and replace it, but it's not going to do you any good. So
exactly.
So we've discussed this, and I think the consensus is that we do expect the chiplet vendors to provide the full production tests, so we can run those at least when you're doing the final test on the device.
Indeed, that's right. Yeah. A sort of post-assembly test and ability to run as much test coverage as you can on that silicon die, maybe through the functional test type stuff or logic BIST or you've also got to check the end-to-end connectivity. But like I said, it's an interesting question that came up certainly when I was doing the panel session as well. Okay, this is an interesting slide where I guess an attempt to sort of try and lock down some physical floor plans really definitely needs some work to try and check the feasibility of this. But I guess trying to come up with a way that you can grow sort of bandwidth or by essentially stamping down multiple chiplets sort of almost next to each other, and kind of a naming convention that kind of tries to indicate how that could work. If you sort of thought of PCI Express, it comes in sort of by 4, by 8, by 16 kind of widths, and so you could think that maybe you buy a by 8 PCI Express chip, but you want to buy 16. So PCI Express is a pretty flexible standard, and you could potentially put down 2 by 8s next to each other to make the by 16 connection, or perhaps you procure a dedicated by 16 kind of chiplet die. But of course, it needs twice the bandwidth, so it's maybe twice the width, and so that's what the sort of the kind of X dimension scales to allow you to kind of increase beachfront to the sort of main logic die to obviously give you more bandwidth per millimeter.
So is this width kind of for just the die-to-die interface, or for the entire chiplet?
Okay, yeah. So this was kind of driven by the die-to-die size and side. So whatever your die-to-die unit is, that gives you a sort of bandwidth per millimeter in by or open HBI, and then if you want more bandwidth, you grow by an increment of that die-to-die PHY instance, and
okay,
you can kind of keep on growing. Yeah.
All right. So this is just for the interface. It's not for the entire chiplet. You just want, if you're abutting the chiplets, you want to have the die-to-die interface is roughly on the same pitch, or ideally on the same.
That's
pitch.
right. Yeah. But then
Okay.
I guess so. Yeah, that sets one dimension. You know, as you said, you're stamping down your instances of the die-to-die PHY on it to maintain a certain pitch. But I guess, you know, we would still want to control the overall dimensions of the chiplet, but by allowing variability in the Y dimension, essentially.
So Ben, where do you see the role played by foundries in this? I mean, TSMC has rolled out their STAR program for info and CoWoS, where these are standardized interface formats.
Yeah.
Foundry is playing in this and maybe driving this market.
Yeah. I guess. Okay, I'm not too familiar with that particular concept, but I guess is that really just defining again the die-to-die interface side, but still not really taking care of the final product? You know what is the physical thing we're buying?
Yeah, the STAR program from TSMC, as I understand it, I've only seen some information, but it stands for standard architecture. So as opposed to providing a technology that you can use any way you want and assemble your own fantastical set of chips and arrangements, they've come up with like 6 layouts, you know, a chip in the middle and 4 HBMs at each corner, and another variant. You know, they come up with like 6 variants that they can provide as sort of a standardized configuration that is more or less has that some level of verification, or at least feasibility from a thermal point of view, manufacturing point of view. And so you pick, you know, option A, B, C, or D rather than making up something on the fly.
Yeah, because I mean, if you went to a picture that looked like this sort of orange thing, you know, you're tessellating and tiling dies all over the place. I mean, it's awfully complicated thing to assemble in the first place, and you know, just matching all of those design rules and thermal expansion, you know, everything to do with assembling such a mismatch of die shapes and sizes could be awfully hard work in that particular case. So, but I guess, you know, I suppose what you described there certainly covers, I guess, a set of use cases. You know, if you happen to want HBM, then yeah, maybe you want a system with 4 HBMs, and as you said, hey presto, TSMC's got a package and an interposer design and everything else that matches that particular application. But I guess not everybody wants that particular form factor.
So is this STAR program intended to go beyond HBM for general chiplets, or is it right now just?
These are configurations for their 3D fabric, as they call it. You know, other foundries have similar programs. Samsung has a similar program, and now of course Intel with their Foveros architecture. So, you know, since they're making the chips and they're making the interposer and they're proposing the architecture, they're sort of elbowing the OSATs out of the market, right? They're sort of taking over the whole 3D packaging and assembly part of it rather than farming it out to an OSAT. So it may not come to that. The OSATs may, you know, find a way to preserve, but the market's definitely going through a big upheaval and quite an inflection here, and I think things are going to change. Yeah.
And yeah, I guess there's still sort of your traditional organic substrate kind of systems. You know, again, where perhaps chiplets could work in that space as well. I'm sure.
So is that what Google is looking at, that like an organic layer to connect them together, a classic PCB board type interface, interposer layer?
I couldn't tell you, to be honest. But yeah, I guess I'm sure TSMC don't want to get into that business of you know, organic substrate kind of assembly. That's definitely the OSAT's sort of area of expertise. But I mean, I can see, the advanced silicon-based interposer type work, that keeping that in the foundry would seem, a reasonably obvious kind of thing to do, wouldn't it? Because I mean, it's a pretty complicated assembly. There's a lot of moving pieces in that puzzle, I guess.
Yeah. Okay, thank you. I was just curious on your perspective.
Yeah. Okay, finally, a quick note on the transport layer. This is really where the application-specific side of it really starts to come in. There are so many different ways to interface IPs, and particularly on the I/O side, listed lots of potential application spaces there that would all need to be solved if you were trying to, again, commoditize chiplets into sort of particularly standards-based interfaces. I think they're all pretty valid use cases in some shape or form, depending on what everybody's building. But the specifics of how you, obviously this is key to interoperability. If you end up single sourced on the chiplet, that doesn't really help the ecosystem, and so I think this is going to be the sort of area where it's going to need pretty careful specification at the sort of application level, in terms of if you want a PCI Express type chiplet, then you're going to have to almost write a pretty substantial chunk of text to say exactly how you transport PCI Express data from one chip to another, for example. But again, it does lend itself quite nicely to sort of future roadmap and that kind of thing as well, in that you can now swap chiplets and kind of change protocol if you really wanted to. Well, I guess within reason. But so I think, again, the ODSA has some work in this area, and I think it was talked about recently as well. There's a sort of proposal to try to standardize this into a generic transport mechanism for die-to-die data, which could be quite interesting. That could certainly help to remove a lot of these different permutations and combinations if there was sort of just some generic means of moving data from die to die.
Those ARM buses, I thought they were just for internal. So are they actually considering them for die-to-die type interfaces as well?
I mean, in some systems, I think you could envisage that happening. In the sort of use case I talk about here, the accelerator type use case, maybe you're using an ARM bus across the die-to-die connection because ultimately that gives you a flat memory map, essentially. Your CPU system could see the chiplet as just another memory mapped part of the system, or if this die was full of SRAM, the CPU would want to see that within its sort of flat address space. So those ARM buses are one way to achieve that. There are open source system buses available as well. I think it's an application that could potentially be used.
Interesting.
I mean, it's okay. No, I won't go there. Okay. Okay, and then sorry.
There's also one that's pretty popular, Open HBI HBI, which is borrowed from HBM.
Indeed. Yeah, that's right. And that PHY, and then I think the sort of generic protocol that I talked about is built on top of Open HBI, and so that I guess standardizes at least the die-to-die part of it. You still got to think about how do you then map this generic protocol into a specific application space. Just getting the data from A to B is easy enough, but then you've still got to work out how do you determine if they were PCI Express packets or Ethernet packets or something like that, I suppose. So you can move the problem, I guess, but you've got to solve it somewhere.
Yeah, do you put it in the chiplet, or do you build a PHY chiplet with that built in? Yeah,
that's right, exactly. Yeah. And then this one just touches on the high-speed sort of interfaces. Like I said, one of the applications is obviously where data leaves the chiplet and goes somewhere else, and so there are plenty of ways in which data could get on and off of a chiplet. Generally would leverage existing protocols, I think. Okay, I think this is the last slide. This is basically sort of an example system from the specification, just kind of describing how you might build this an open chiplet based system, I suppose. Obviously doesn't really imply any kind of real product or otherwise, but certainly a number of chiplets doing a function, with data getting on and off the sort of main system through some more chiplets as well. So I think that's basically it. Yeah, like I said, the specification is out on GitHub. If in terms of contributing to it, it's definitely worth reading. The repository includes a description on how you can contribute to it. So because it's still hosted within Google's domain on GitHub, there's a thing called a contributor license agreement, which basically just says that if you're going to work on it, you're doing so in a collaborative manner. I think a lot of CLAs are already in place with most sort of big companies, because obviously Google has quite a lot of open source projects out there already with a lot of people contributing to it. But definitely have a read of the material in there. It's Apache 2 license, so it is it's available for whatever you would want to do with it, basically, I suppose. Okay, I think that's about it. I nearly filled the hour.
That was good. Quick question for the physical description of the bump locations. Is that part of the spec? Is there anything in there that?
Sure. I mean, I think it ultimately would need to become part of the spec. That's right. If we really want to get to the point where we can almost put out the open chiplet as a design specification and say,
Well, we are working on that. My question is, do you have a draft of something that we could look at? Or?
Oh yeah, no, definitely not. No, it just
okay.
Currently, just that sort of Lego brick style concept, I suppose, as to how that could work with a potential ball map. I think what's nice is that if you allow adjustability in the Y dimension, then obviously it gives the suppliers the scope to trim down the size depending on the amount of content on the chiplet itself. But also, those balls could just be power and ground, I guess. So as the die increases, you kind of get more power and ground balls. But the periphery of the chiplet on certainly on the top and bottom edges could pretty much stay the same regardless of how the Y dimension changes. I guess kind of assumes that there's no sideways sort of interconnect between the chiplets. That there could be, but anyway, that was another part of the thinking there.
Okay, thank you.
All right, Ben, thank you very much for this presentation. I appreciate your time and spending time with us. Are there any other questions from anybody else? I think I can stop recording now, and then